Before we start, this is a warning for the laptop users trying to open my Fusion files. Due to its complexity, the motion studies inside the final assembly file will not run smoothly if opened on a laptop. Instead, I suggest you to go into Design, then Assemblies, and open any one of these Fusion assemblies which make part of the final assembly, as their motion studies are much less computation heavy. Now, this is our Mars rover. It is called BMO, named after this goofy character from the cartoon series Adventure Time. Now, BMO stands for Be More, so we focused on making our rover more science-centered, meaning we aim to make our rover to be more compatible with various lab equipments. Now, let's begin from the bottom, the wheel. BMO's wheels are combinations of both Curiosity's and Perseverance's. It takes its barrel shape from Curiosity's wheels and the parallel treads from Perseverance's. The barrel shape lets the wheel grip even when the surface is slanted relative to the direction of rotation. The parallel treads were shown to be more puncture resistant at the Jet Propulsion Laboratory. We also added in the odometry marker from the Curiosity rover, which actually spells out BMO in Morse code. This odometry marker helps determine whether the rover's wheels are slipping and adjust the actuator voltage. The wheel is attached to a motor shaft using 6 M20 by 2.5 metric heavy hex bolts. Now we have the suspension system combined with a working differential mechanism. This part is nearly identical to both Curiosity and Perseverance, in which the suspension uses a rocker bogie structure and the differential mechanism uses the differential bar. The differential mechanism implemented here averages the angle the two sides of the rocker bogie structure make, stabilizing the rover's main body and whatever volatile things it has inside. That magic happens right here at the connection point between the suspension and the differential bar. Here we struggled a bit to figure out how many degrees of freedom we needed, but we found out that both Curiosity and Perseverance uses a hard rubber instead of rigid bodies here. So we added in 5 degrees of freedom to mimic that behavior with rigid bodies. It is worth noting that since there are so many points of revolution, each shaft and hole are set to H9D9 free running tolerances to compensate for the large friction. Now for the arm. Here we basically decided that just putting a claw at the end of the arm is too boring, so we made it into a multi-tool arm, mimicking Curiosity's arm. The arm itself has a 5 degrees of freedom, allowing it to reach the rover's main body to drop off samples it collected from the ground to be researched. The multi-tool arm itself consists of a claw, a grinder, a drill, and a full spectrum camera. This allows the lab equipment on board BMO to do research on not only ground samples, but whole rocks and core samples of the ground for geological analysis. The multi-tool hand is a hexagon shape, allowing for up to 6 components to be filled. We filled the remaining 3 slots with temporary replacements for whatever scary lab equipment scientists want on BMO's arm. For the shaft hole tolerance, we used H8 F7 close running for a more accurate maneuver since we don't want the multi-tool arm to bump in anywhere. Now for the solar panels. The deployment of this solar panel array is probably the most pleasing visually, but was the most nightmarish thing to create on Fusion. This concept of a retractable origami-style solar panels came from NASA's InSight Mars lander. Here we can see that NASA uses a non-rigid cloth-like material for its solar panels, so we had to figure out how to make this work with only rigid bodies. When deployed, this solar panel can generate up to 700 watts on a clear day, which is more than 6 times the wattage provided by the MMRTG power generators mounted on Curiosity and Perseverance. By implementing a vacuum cleaning system in these solar panel covers, we can increase the longevity of the solar panel as well as allow for larger energy-consuming and long-term lab equipments to operate on BMO. The shafts here that raises the solar panels are H8F7 closed running tolerance, which acts as a suspension to protect the solar panels from sudden shock. Lastly, we have the rover's head and antenna. BMO's antenna is relatively simple with 3 degrees of freedom, allowing it to point its high-gain antenna wherever it wants. Since this motion needs precision, the tolerances here uses H8F7 close running. For BMO's head, we suspected that there will be fragile equipments handling optics on a micro or even nanometer scale, so we added a mechanical iris as a way to shield these high-fidelity equipment from their environment. The 2 degrees of freedom the head has allows it to point towards anywhere except directly below. BMO's neck is responsible for retracting and deploying the head. Both the neck and the head uses H8F7 close running tolerance for precise movements.